Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying AOD lecture 5. So this is our last lecture for the AOD series and post that we'll be starting with indefinite integration. So let us directly jump into the discussion. We'll be studying about second order derivative test for local maxima minima for derivable functions. So we have three cases over here. First is local maxima, second is local minima, and third is the case where actually the test fails. So let's look at the case one, that is local maxima. Local maxima looks like this, right? In case of derivable functions, not talking about indifferentiable functions. In case of differentiable functions, local maxima looks like this. So the first step is to obviously calculate the dy by dx equals to 0. Let's say we get a point x equals to c for this. Now we have to calculate d2y by basically double derivative d2y by dx square for x equals to c. Now in case of local maxima, we'll be getting that as less than 0. For local maxima, it's less than 0. So how do we remember this? Sometimes it becomes confusing that for local maxima it's greater than 0 or less than 0. For that, we can remember it with this kind of curve. So basically this curvature is pointing downwards. This curvature is pointing downwards. So for downwards, we have negative y-axis. So for negative y-axis, we have less than 0. Similarly, we have our case 2 local minima. For that, d2y by dx square would be greater than 0. How? This. So basically curvature is pointing upwards. In that case, we have d2y by dx square as greater than 0 at the point of where dy by dx equals to 0. Now the third case is very interesting. We have case 3 over here where dy by dx equals to 0 at let's say x equals to c, and also d2y by dx square equals to 0 for x equals to c. Now we don't know if we have a local maxima or local minima because we need an inequality over here. But we are getting equality with 0 at x equals to c. So for that, we'll revert back to first order derivative test. Basically, we'll be plotting the number line. This is x equals to c. And we'll see some point over here and we'll see some point over here. And we'll see if the slope was positive or negative. Let's say in this case, it's positive. So we'll have a maxima over here and a negative slope over here, right? So if second order derivative test fails, we revert back to the first order derivative test. Now let us look at one example to understand the process. Find the points of maxima and minima of the function fx equals to this. So the first step is to calculate the f dash x. What that would be? 60 times x raised to power 4 minus not yeah 60 times x raised to power 4 minus 180 times x cube plus 120 x square. So that would give me 60 common into x square multiplied by x square minus 3x plus 2, right? Now this eventually gives me x square, x minus 2 and x minus 1 multiplied by 60. So basically we have got 3 points, x equals to 0, x equals to 2, x equals to 1. We have to calculate f double dash at all these 3 points. Let's try to find out. So let's write let's write f double dash over here. F double dash would be, we have 60 as common, we'll be getting 4x cube minus 9x square plus 4x. This is our f double dash. Now let's try to find out f double dash 0. That would be 0 because we have x over here, so that would be 0. F double dash 2, that would give me 60 times 4 into 8 minus 9 into 4 plus 4 into 2. So that is 8, that is 32 and that is 36. So this comes out to be positive. So this would be greater than 0. And f double dash 1, that would be 60 times 4 minus 9 plus 4. That gives me a negative quantity, that would be less than 0. So for this and this, it's clear that this is the case of minima and this is the case of maxima. But for this, we have to revert back to our first derivative test. Let's look at that one. So our f dash x was 60 into x square multiplied by x square minus 3x plus 2. This was our f dash x. So this is our number line and we have this point 0. So let's take one number on the left hand side and one number on the right hand side. So we have minus 1 by 2 over here and we have 1 by 2 over here, let's say. So we are getting, this is positive only. So let's write it as some positive number k. K times x square, that would be 1 by 4 minus 3 into minus 1 by 2 plus 2. So this overall becomes positive, this is positive, this is positive, and this is positive. So this overall becomes positive, right? So f dash is f dash minus half is positive. Now f dash 1 by 2. So this was 1 minus 1 by 2. And f dash 1 by 2, that would be k times 1 by 4 minus 3 into 1 by 2 plus 2. Now that is again a positive number. So this is also positive. So basically x equals to 0, we have got a point of inflection. Like this is the positive slope, this is 0, and this is positive slope. So this is the kind of point we have got at x equals to 0. We haven't got a maxima, we haven't got a minima, we have got a point of inflection over here, right? Now let us move on to next topic, Rolle's theorem. So Rolle's theorem says that if fx is continuous function in a to b, fx is also a differentiable function in open a to b, and f equals to fb. In that case, there exists at least one point x equals to c for that f dash c is equals to 0. In the range c is greater than a less than b. Now this sounds too complicated, but if we try to plot it on the graph, then it becomes too easy to understand. So let's do that. Let's say we have a function and these are the points a comma b. So these are the two values. This is fa and this is b. Let's write it as fa and this is fb. And fa equals to fb as per the given condition. Now let's try to plot a graph which is continuous between these 2 points. Let's say I'm drawing one graph, continuous and differentiable. So this is one of the graph which I can draw being continuous and differentiable between these 2 points, right? Now, as we know that fa equals to fb, this straight line, this would have slope equals to 0. This would have slope equals to 0, right? Because it's a straight line and both the values are equal. So it's a flat line basically. Now, I can clearly see that there is one point over here where f dash becomes 0, where basically slope becomes 0. So that is the whole point of this Rolle's theorem. It says that if we try to plot a function which is continuous and differentiable between 2 points which are equal, in that case, we'll get at least one point over here between A and B. Let's say this is C, then f dash C would be 0. Now let's try to make it more curvy. What do we get over there? So this is our FB. So let's say if I try to make a curve like this is also differentiable with no sharp edges, and this is also continuous, right? So we are getting 3 points over here, 4 points actually. This one, this one, this one, this one. All these points have a slope equals to 0, and that slope is nothing but slope of this line. So we have got at least 1 point of x. Now, what kind of questions can be framed with such a theorem? So questions are very simple. Basically, they'll be asking you to calculate the applicability of Rolle's theorem in a particular set of equations or functions, right? So that is the only type of questions you can get in PGDBA. Now let us talk about Lagrange's mean value theorem, which is nothing but a superset of Rolle's theorem. Now, what does this Lagrange mean value theorem says, or LMVT says, is, let's say again we have a curve over here. We have 2 points over here basically. This is A, B, but now it's saying that both might not be equal. So this is FA, and let's say we have B over here. This is FB, right? Now, if we try to plot a graph which is continuous and differentiable between these 2 points, let's say I'm plotting a graph like this, then we'll have one such point which will have the exact same slope as this slope. So this slope, how do we calculate this slope? If we remember the basic coordinate geometry, we can easily tell that this slope is nothing but FB minus FA divided by B minus A. Basically, this distance, this distance is B minus A. This distance is FB minus FA. So FB minus FA divided by B minus A. This is the slope of this particular line. And LMVT says that if we try to plot a graph which is continuous and differentiable between these 2 points, then we'll get at least one point where we get a slope we get a slope at the point on a curve that is equals to the slope of this particular line, that is fb minus fa divided by b minus a, right? So that is also again very intuitive. What we did, we just moved this point. In case of Rolle's theorem, this point was here. What we did over here, we just moved that particular point to here, and over there slope was 0, and that's why we were comparing it with the slope equals to 0. But over here slope is this, so we are comparing with this. So it's just a modification or basically superset of Rolle's theorem. Now again we can get a curvy curve like this one. So we will have 3 points over here in this particular range that will have the same slope. So there exists at least one point. So this was all about LMVT and Rolle's theorem. Let's see one example. So this is the kind of question you can get in PGDBA. In 0 to 1, Lagrange mean value theorem is not applicable to. So in this question, what we have to do, we have to just check the conditions, like if the function is continuous and differentiable in this particular range. So let's start with option D. We have mod x. We know the graph of mod x is like this, but we are talking about the range of 0 to 1, in the range of 0 to 1. So over here, we can clearly see that mod x is continuous and differentiable. So LMVT can be applicable over here. Similarly, x mod x. So mod x is just, it's a formality over here because we have a positive domain over here. So that's why we can write x mod x as x square. So this is nothing but this graph only, not this, only this graph only, right? In the right hand side of origin, we have this function as x square only. So again, we can clearly see that LMVT can be applicable over here because this is continuous and differentiable in this range. Now, third B option, fx equals to sin x by x for x not equals to 0 and 1 for x equals to 0. Now let's try to do it. So basically, we know that in case of x becomes infinitesimally small, this becomes close to 1. So at x equals to 0, we have value as 1. And even if we just move a little away from it, then also this particular function will have the value close to 1 because of the limit, right? So we know that this function is continuous at the border point at 0 and 1 as well. At 1, it's definitely continuous, but the critical point was 0. So at 0, we have RHL as 1, and we have the function function value as the 1 as well. So that is why this function is continuous at the endpoints, and it's also differentiable because it's a smooth function, right? Sin x by x is a smooth function, that's why it's differentiable. So LMVT is also applicable in this particular function. Now we talk about A option, 1 minus 2 minus x, 1 by 2 minus x less than half, and 1 by 2 minus x whole square, x greater than half, greater than equals to half. In that case, we can clearly see that at x equals to 1 by 2, both the values are different. So the function is not continuous at x equals to half. So that's why LMVT is not applicable in this. So we have the correct option as this one. So this is the kind of question you can get in PGDB examination if you are concerned with LMVT and Rolle's theorem. That is the maximum you can get. So today's lecture was still here only, and we have finally completed the Edu series. And after that, we'll be starting with indefinite integration. Let's meet tomorrow. Thanks for watching.